So I wanted to start this morning by highlighting, in fact, two endeavors that we have running at the moment. There is one called the Advanced Quantum Testbed. That will be the bulk of the slides that I present. This is a research effort that is exclusively to our group at Berkeley and Lawrence Berkeley Lab. And at the very end, I will also show a slide or two on the new Quantum Center that we have been awarded, and that's a national effort across 15 institutions in the US. So just a few words about the philosophy of the AQT. I've been working on superconducting qubits more than 20 years now and superconducting circuits. And it's always the fundamental questions that have motivated me. How do you measure a quantum system? How does quantum meet classical, things of this nature? And as we all know, the field has been growing very rapidly into this technological direction of how to harness entanglement for building quantum machines. So there are very many crossroads in this field. And as an academic, one has to think a little bit about, what are the problems that you want to solve? What does one view as sort of the most interesting and most game-changing questions? And at least for me, about a few years ago, it really sort of sunk home that we really have not found the perfect qubit. We have not only not found the perfect qubit, I think we haven't found the perfect technology to build that qubit. And I think it's still questionable what is the perfect application for that quantum machine. And if one sort of takes stock in that statement, and that's really a reflection that there are many fundamental questions in this field. And what I wanted to do was go beyond the limitations of my own group, which was about 20 people at that time. And from there, we found a great partnership with the Department of Energy in building what we call the testbed. And the testbed idea is that we are able to stand up a full stack, albeit small scale, of course, quantum system, starting from chip, the fridge, all the control electronics, etc., but in a way that we can partner with the community to swap out any specialized technology. So we can swap out the qubit, we can swap out different algorithms, so on and so forth. And in this idea, the experiment was to sort of expand the reach and broadly survey quantum phase space. So in a nutshell, that is what we were trying to do with the testbed. So now let me share some thoughts on it. So the mission is really to assemble the state-of-the-art in superconducting quantum computing hardware to address key basic science questions that are needed to develop robust and extensible quantum systems. So this starts with a broad exploration of quantum technology. We are not wed to one particular qubit design, one particular connectivity, or even one class of algorithms that we wish to execute. One thinks about, well, we don't really have a universal computer. Can we go ahead and have bespoke processors? So we are happy to build a processor that has connectivity or other type of topology that's specialized to a problem. So in particular, what we're saying is we don't have to necessarily solve, at least in my mind, the most universal of problems. Let's try to solve a few problems that actually show advantage. There is also a pathway in the AQT to integrate hardware. So there are folks in the ecosystem that think about how to have better control systems, better wiring, better cryo packaging, so on and so forth. And as I'll show you in a few slides, there is a way to integrate these in parallel into the testbed. We have a growing library of processors. We have 2 or 3 topologies that we build ourselves, but we have partnerships now with MIT Lincoln Labs to look at different type of architectures, and also with companies in the ecosystem also now entering the field of building different quantum processors. And at the end of the day, when we assemble this hardware, it is not trivial to go ahead and run a state-of-the-art quantum computation, especially if you're trying to optimize for gate fidelity, gate depth, trying to correct for noise sources, etc. So we have a team on the ground that partners with our users to go ahead in a scientific collaborative fashion to get the maximum out of this hardware. And very recently, we've started to then open up to user applications. Just a few weeks ago, we went live on the website with this. So in a nutshell, these are the pieces of the AQT. So let me delve a little bit deeper into the technology that we have running. So in my own lab, I have 7 dilution refrigerators that are running. This is number 8, which is dedicated for the AQT. So this is a 1000 microwatt or milliwatt dilution fridge. I'll go a little bit into the details of how we planned out the cold stage and the cryo packaging for this instrument. But beyond that, in terms of control electronics, we have really 2 pathways for the controls we are pursuing. And again, we are driven by the idea that a lot of questions, if not many or most of the most fundamental questions, can be answered at the level of, let's say, 10 to 100 qubits. So at that number of qubits, I can simply buy a control system. let's say from Zurich Instruments, and brute force my way to control 100 qubits. At the same time, we do want to look a bit forward. Such endeavors are expensive and perhaps difficult to scale to thousands of qubits. So we have our own team on the ground that works with accelerator controls. And they have very recently been able to put together custom FPGA boards with optical interconnects that will allow you to scale to thousands of qubits without difficulty. So we are pursuing both pathways in parallel. And finally, in terms of the processor units, they are typically three-dimensional at this moment. And I'll share with you a few different thoughts on how we bond these chips together. And I think perhaps the most valuable resource of any of these teams are the people. So you see some happy graduate students on the right, hanging underneath the fridge trying to put it together. So the next three slides are a bit text heavy. I apologize, but I think they are necessary to give you a sense of what the main foci and science drivers are in the AQT. So the endeavor is broken into three thrusts. The first one is focusing on quantum computation. And these are four problems, or four classes of problems that we're looking at in great detail. The first one is in the domain of quantum chemistry. And there are two classes of algorithms we're looking at. One is the variational quantum eigensolver, or in this case, trying to do estimation of ground states. The other one is also to look at imaginary time formalism for quantum states. So let me just say one quick word about both of these. I think there may be an interest from the community in both of these. So VQE has basically the idea that we go ahead, build a quantum machine with a certain set of knobs. Each configuration of the machine is a computation. It figures out the energy associated with that state, and then you twiddle all the knobs till you find the minimum energy. Now, the challenge is, can you efficiently service and find that phase space, and how accurate is your estimate? And that is rather an unknown question still for VQE. The other fundamental question is, will you actually have quantum advantage in a VQE algorithm in the quantum complexity sense? Also not known at the moment. Kite is a rather different algorithm, and this says that all your eigenvalues, typically in the quantum domain, are of the form e to the minus I omega t. So this is an oscillatory function. If you go to imaginary time, that e to the minus I omega t goes to something like e to the minus omega t, right? And it's a decaying exponential. And the ground state will be the one that lasts the longest. So in fact, you can just go ahead and monitor your system at a certain time and you will get the ground state energy. And this doesn't require any ansatz or survey of phase space, etc. So two very different approaches to chemistry. One can also look at simulations of highly connected matter in field theories. And this expresses itself in terms of either condensed matter physics, in terms of topology, or high energy physics for information scrambling or gravity and so on and so forth. So again, this is basically a type of quantum simulation where you're using the connectivity and highly interactive nature of quantum systems to do a calculation. Two other more nuts and bolts pieces that go into this, we have successfully implemented three-level logic, or Q-trits. And there's many advantages to using 3 levels instead of qubits with 2 levels. One is simply that your Hilbert space is bigger for the same hardware for transband qubits. You have flexibility on your gate set. We can do a lot more different types of rotations. That's a bug or a feature depending on where you are in the developmental curve of this Q-trit technology. You also can access with greater efficiency certain algorithmic encoding. So typically with qubit systems, it's difficult to get 3 or 4 qubits talking to each other at the same time. Wiring is challenging. If you have a Q-trit, in fact, you can have a higher level of connectivity graph, even if physically they're just nearest neighbors. And finally, all quantum systems are looking at how to benchmark, verify, and validate the quantumness of your setup. So of course, we are also benchmarking many such protocols in this direction. Processors, as I hinted to, we are looking at 3D integrated devices. Perhaps the cleanest one is flip chip because you simply have air between your 2 chips, but nonetheless, there are some limitations to not having wires between your 2 chips. We are specifically looking at, for us, this atomic layer deposition, very, very thin membranes that are grown layer by layer. And they can allow us to put circuitry on both sides of the membrane, or also to have little terrace type structures for additional 3D complexity. And of course, one needs crossovers and air bridges for this. We again focus on amplifiers to read out these qubits. We have been working heavily on resonators to improve materials. We have now 4x improvement in planar resonators, 6 million plus Q, allowing us to sort of remove these oxide surfaces and tailor them in a way that increases coherence. And of course, we are also looking at, on the lower right, many different types of 2-qubit gates. And again, I'll give you a snapshot of a few of these as I go forward. Okay. And finally, sort of zooming out, starting from the processor to the cryo package outward, there is the question of how do you control this? And as I alluded to, we have control hardware that has 2 different pathways, homegrown and purchased. We are starting to now go a little bit further in terms of what that control hardware does. So looking at instruction sets that we program into the FPGA, more complicated functions that are now put into the actual hardware stack itself. And there's a lot of work being done on the lower right on cryo packaging. We want to get the maximum coherence out of these devices. All right, so that was sort of the text heavy slides. I apologize again in retrospect for those, but now hopefully I can go into a few slides to give you a snapshot of the science that's going on. So this is the current generation cryo package. And I think one of the real fundamental challenges in quantum information science is to maintain the entanglement that you want, right? So first point is to create it, right? That already is a challenge. How do you do the gates, so on and so forth? But then you don't want the highway robbers to take away your entanglement, right? And this can happen from neighboring qubits, from the environment, from the box, from radiation, all sorts of other things. So here we've spent, in partnership with a company called Bleximo, quite a lot of time. And in fact, they have done the heavy lifting and designing this type of cryo package shown here. This is able to accommodate 40 RF lines. So this is a 16-qubit-ish type of package. And you can see the simulations on the right showing you the matching and the crosstalk. So that's in a log scale in dB. So the matching, the through, this is the blue line. So that's actually very well coupled, right, with 0 dB. The crosstalk or reflections that you get coming into the port are below minus 20 dB all the way up to 10 gigahertz. So that's pretty good, meaning that 1% of or less of your information is reflected. And then on the bottom is the critical crosstalk spec that we are all struggling with. I think in the community, you drive one control line, you excite the neighboring qubit, right? And there are many reasons for this. So the red line, the red qubit is the thing that you're exciting. So that's coupled with 0 dB or unity efficiency. And the sort of the different colors at the bottom show you what happens to the first qubit if you excite another line, and that's 6 orders of magnitude down. So in principle, one would imagine that this design is very good for crosstalk. I should say the first designs, we also wanted to, as a physicist, I asked Alosha Marchenko, can you actually simulate the box we already had, which has bad crosstalk, and really find the sorts of bad crosstalk? So indeed, he found many modes that were bad. So I felt ashamed, but happy at the same time. At least he was able to find the modes for this crosstalk. So the fridge, it's wired up for 128 qubits. Okay, that's the number of lines we put in to start. So it's 160 coax lines, 16 superconducting amplifier readout chains are there. However, if you build a 128 qubit chip, at least for us, we will not have a Hilbert space corresponding to 128 qubits. So we thought it was more relevant for us to break this fridge into 4 chambers. And you can see them pictured in the middle section with those cans on top of them. And the idea is that I can run 4 32-qubit processors in parallel. And again, this goes back to the idea I was presenting in the beginning. We can run different qubit architectures side by side in parallel. As we continue to warm up the fridge, we can change one of the bays, 2 of the bays, depending on what's happening. You know, and when we bought this fridge about a year ago, I thought, wow, this is quite a lot of space. For the last 3 months, I've been hearing from the group, we need another fridge, right? We already backed up with more qubits. So I don't know where it ends, how many fridges one needs, but at the moment, this is still being used sort of 24/7. This goes a little bit into greater detail. You can see how all the wiring is done in a very modular fashion with all the filters and so on and so forth and amplifiers. This is, again, all Alexei Marchenko's handiwork, and I think he's done a fantastic job wiring up this fridge. It was the first one I didn't wire myself as a scientist, so it was an interesting transition, but I'm very happy. I don't think I'll ever wire a fridge again. Here's a critical piece of this. One requires quite a lot of shielding, especially if you want to get T2 high, and I'll show you some numbers in a moment. So we typically use multiple layers of both magnetic shielding and superconducting shielding, and there's the vector map showing you where the remnant fields are in such shields. Okay, control systems. So here is the first prototype assembled by our Accelerator Technologies group. And it's based on, if I remember correctly, a Vertex 7 FPGA system. They have different ones. We are not at the ASIC level yet, although we can execute on that. We're waiting for that because I don't know exactly what functionality I need in the control system to build an ASIC. So I think we're sort of dragging our feet a little bit, just using commercial FPGAs and test boards. But I think what's interesting about this particular system is the cost profile of an FPGA, you know, is for 8 channels or 16 channels. That's typically what you buy for a certain cost. So if you say I want 64, 100, 256 channels, this is a tricky business. One can take many different FPGAs, electronically combine them together, right? This is typically what you see in the field, and that's a very useful technology. We have it. But these accelerator folks are very good, in fact, at putting delay generators together with optical interconnects, right? So the idea came up, well, can you use that technology, go ahead and sync well enough two FPGAs with this optical fiber type of technology? And if that works, one would imagine that you could link many of these modules together. So this first prototype is running. This was an 8-channel prototype. We were able to do everything with this. It was quite an extraordinary work done by the accelerator folks. They can do randomized benchmarking, controls everything in our 8-qubit system. And where we are at the moment is we are in the test phase of these multiple modules linked together by optics. So I think that'll be interesting for us at some point soon. Do the qubits work? Here's a sort of a graphic showing coherence times on average of the devices that we have. So our chip is the one in red. I don't know if maybe you prefer blue or other colors, but I guess ours is the one in red. It should really be a different symbol. But UCB8 is written there on average. So we have well in excess of 100 microsecond coherent time for both T1 and T2 and planar chips. And of course, one has to see if that scales as you go to 3D and onward, and that's an active domain of research. Another thing that's important, again, I think which is common across the field, is that these quantities that I showed fluctuate in time, right? And actually getting stability in your gates and in your coherence times is quite important. So this is a CNOT gate, and this is randomized benchmarking showing standard SRB, standard randomized benchmarking, interleaved randomized benchmarking, and also just the CNOT gate fidelity across this system, measured over 100 minutes, right? Just to show you sort of the stability of the system. So this was a pretty nice plot. You can see the error rate is sort of 0.01, right, for for the CNOT gate, and this is not fully optimized yet. But it's giving us a sense of how we can maintain very good fidelity across all these qubits. And a very interesting question to me is what gives rise to the width of this histogram, right? I mean, what causes these fluctuations? So that's another interesting science question we're looking into. Okay, so coming towards the last couple of slides, where are we in this AQT experiment? So the first step was hardware development. We are in completing year 2 of this project. We started in September 30th of last 2 years ago. 3 years left on this 5-year program. So phase 1 was to develop somewhere between 8 and 32 qubits, show coherence times greater than 50 microseconds, greater than 95 microsecond gate fidelity. So I think I've shown you we've done all of that at this point. We will continue to leverage forward, again, not pushing on the qubit axis, but pushing on the functionality axis, right? The goal for us is to build as many qubits as you need to answer the question that's interesting. So we were for a time in phase 2, which was running circuits, computations, et cetera, to benchmark the hardware. And as I said, as of October 2020, we've gone ahead and gone live on our website with applications for external users. So we have received in the first round 22 proposals, which we are 24, I think, that we are actually now reviewing very carefully and seeing which ones we will be able to deploy as science experiments on the AQT. So I think that's the quick summary of the AQT. I did want to show this last slide or two about the new endeavor that we are also undertaking. So the United States government passed the National Quantum Initiative Act. And this act, amongst many things in the quantum domain, enables people to go ahead and establish, specifically under the Department of Energy, 5 quantum centers, right, that would be running at the tune of $25 million a year. So we have one of these centers. So in terms of numbers, the AQT project is an investment of $31 million from the United States government. This Quantum Systems Accelerator, which we were recently awarded, is a $115 million investment from the US government. The key players and technology and theory leads are shown on this slide. So again, a lot of text, a lot of names, but to give you a sense of the different flavors of science we're covering. There is quantum theory, and the theory piece puts together everything from complexity to domain-specific science. So there is a contingent with Umesh Vazirani, Scott Aronson, John Preskill, Thomas Viddick that thinks about the complexity class of all of these problems, the challenges associated with benchmarking things with supremacy. There are other theory colleagues that think about how do you optimize a particular physical system, whether it be a superconducting qubit, an ion trap, or a neutral atom system. There are theorists that think about the algorithm side. How do you pair a specific bespoke tailored algorithm to the hardware that you have? So we're asking the question, if you build something, what is it good for, right? And how do you prove it? Okay, and of course, different physicalities are good for different things at this stage. They're not universal computers yet. And in terms of the experimentalists, Chris Monroe and others are heading up the ion trap team. Michel KUREK, the neutral atom team. Will Oliver, myself work on the superconducting qubits. Okay, and so there are the 4 technology pieces that we have with Rydberg simulators, atomic tweezers with Junyi at NIST, superconducting qubits with Will Oliver, myself, and trapped ions with Chris Monroe. And the goal is really to complete this co-design cycle. That starts basically here, where you pick an application, right? And here are the applications we're looking at in the center: optimization, machine learning, control theory, aided variational algorithms, etc. You think about the fundamental science. How do you encode that problem? Right? What's the ansatz that you need? How do you execute the algorithm? And then you map that onto a certain set of NIST qubits, right? So you will choose within your drawer of qubits which ones are the best suited for this particular application that you've chosen. Then you put together the rest of the pieces. What are you going to control? Do you need feedback, real-time feedback, etc., on all of these things? And then finally build a prototype that executes that particular calculation. And then you, of course, go around the circle again, right, trying to make it better. So I think this is where I wanted to end up, hopefully roughly around 25 minutes into the talk, and leave time for your questions, but giving you an overview of these 2 large projects that we have running. And thank you again for your time this afternoon. So I'll stop here.
Thank you, Irfan. Very good. Great timing. Thanks very much for the presentation. Very impressive. I have a couple of questions, but first I'll ask mine since I'm here. So how do you see collaboration with both, with the Quantum Systems Accelerator? I think that's a question I floated to you. The Lab Quantique is a not-for-profit. We're working really in support of ecosystem building everywhere. We've got good relationship and discussion with Sherbrooke, for example, Institut Quantique, with others. Is the Quantum Systems Accelerator open to collaboration with non-US entities or startups or industry? How do you see things moving forward?
Right, so we do very much value these partnerships within the US and outside of the US in the industrial domain or in the commercial domain. We are also partners with Alexander Blaze on our team from Sherbrooke. So we have sort of a tight relationship on that level. There are different ways to have partnerships. So for certain vendors, we have CRADAs, right? So there are really industry arrangements to figure out very detailed how to manage IP, how to exchange information, what projects we'll work on together. So we do that with, let's say, Quantum Benchmark, which is from Canada, and also Mike Biersak. We have a relationship with him with Q Control. So there are ways to go deeper into this depending on the level of engagement. So I think we have now a streamlined set of forms for NDAs and so on and so forth, and all these things so that everyone's IP is protected. But we are happy to do this.
Okay, thank you. Well, I'll come back to you maybe with some ideas about the broader animation of the ecosystem. I've got 2 questions. One from Omri Shoshan. What are the biggest challenges you and the team are facing in terms of control hardware and software?
Okay, so in terms of control hardware, we are working in a fridge, right? So this means that there are challenges in terms of how many cryogenic wires you can get in, what's the travel time. So light travels at 1 foot per nanosecond, right? So no matter what you do, there is some tens of nanosecond travel time, if not more, from the top of your fridge to the bottom of your fridge. So if you would like to implement, let's say, very fast feedback, right? You want to go ahead and measure the state of your system and then actuate a change based on that, then you have to fight this delay. You also have to fight the delay inherent to your FPGAs, which is also not short. Hundreds of nanoseconds can be a typical delay. So if you want to do fast operations, that's a fundamental issue at the moment. In terms of scaling up to number, again, it's a question of scale. At the level of 100 qubits, 100 physical qubits, I think the problem is manageable to answer other physical questions that you have. If you really want to think about scaling to 1 million qubits, then the following multiple questions come up. How do you convert between quantum coherent information and classical analog and digital information, right? At the end of the day, you're going to get a digital signal out. Where should this happen? Should this happen at the coldest part of your fridge, higher up in your fridge? How can you multiplex? How do you frequency multiplex? Where is all the crowding? So all of these questions, of course, are very, very big proverbial elephants in the room, right? And I sort of swept them under the rug saying that, look, at the level of a few hundred, I'll just brute force it and answer the other physics questions. But indeed, I think perhaps your question is getting a little bit at, where are the real challenges when you scale beyond 100? And those are the ones that are there.
Yeah. And another question for me. And so will you go beyond 128 qubits with this setup? the AQT, how big do you want to make your processor with the current fridges and everything that you have?
So, and again, of course, there are advertisements of very many numbers of qubits out there in the wild. Yeah. And I think, again, the optimization, the driver for me is what's the science you want to do, right? So first you have to tell me the application, which will be a fundamental science question that cannot be answered with 128 qubits. So, and that means that I will have exhausted all the questions that I can do with 128 qubits, which will certainly take some time to get there. At one point, I sort of was alluding to this tongue in cheek with the number of fridges. I'm tired of buying board-built fridges. I think this is not the right, not the right approach to scaling these. So I think this scale of fridge, I told the Blue Forest people, probably the colleagues at Blue Forest, this is probably the largest fridge I think I want to buy at the moment. After this, I needed to make better use of my wires, right? So I think beyond 128, I will be actively looking at multiplexing, modules of different chips. Maybe you link two 128 qubit chips together, so on and so forth. So I think we need to think a little bit more about what that architecture looks like.
Okay, thank you. And so I think I'll take the last question. Maybe a naive question. You said that you can run a 128 qubit section as 4 different sections. Do you run them? Do you run independent tasks? If not, how do you sync them?
Right. So right now they're running independent tasks. So in fact, I'm using even different processors in them. It would be a very interesting idea to think about modular quantum computing, right? So the ion traps folks think about this, right? Here's one ion trap module, and then you can use photons to naturally link 2 ion trap modules. I don't think this has been done yet, but clearly that's an idea out there. With superconducting qubits, that would be a bit different, right? If you want to actually just get the timing right in some passive sense, that's no problem. We can have a master clock that syncs these 4 pieces. But if you want to distribute entanglement between them, and have distributed computing, that would be a tremendous output. But I don't, at least I'm not there yet. That requires quite some thought in terms of how to transduce information and send it across physical distances.
Yeah, okay. And last questions. I have many questions, but that will be for another time. So, but last question, is it possible to use the current qubit computational capacity to advance the circuit design?
Can you say that once more? I missed one middle part of it.
I think, so is it possible to use the current qubit computational capacity to advance the circuit design? Yeah,
so I'm not sure I'm interpreting the question correctly, but there's two ways that I can see this. One is that can you use qubits to design better circuits, right? So if you were actually thinking about running a computation, some kind of complex optimization, the qubits are not powerful enough to do that. Your classical computer will do better on that. What we can do, of course, is use them as, for hardware simulations, if you like. I put together a qubit, I run different types of interleaved randomized benchmarking, and I can figure out all sorts of different crosstalk channels or other channels that are causing decoherence. And based on that information, I can invert the matrix and design the next generation of processor. So that we actually do, and is actually quite powerful in trying to figure out, where the holes are, so to speak, in your entanglement fabric.
Okay, excellent. Okay, so thank you very much. I think we're good on the questions. Looking at the Q&A, thank you very much, Irfan. It's been great to have you today. Look forward to further interactions with your many initiatives, and good luck with the good qubits. Have a great day in California, and thanks for being with us this morning. Thank you.
Thank you again.
Our next speaker will be Michel. So Michel will introduce himself. So Michel has been working with us at the Lab Quantique on a report that is delivered a couple of weeks ago, working on several aspects, and I think gives a good overview of the dynamics in the quantum field. Michel will have 25 minutes or so to give us an introduction, and the report is obviously, you can download the report on the website of the Lab Quantique. The address will be there somewhere, and I'll post it also in the Q&A session for those who don't have it yet. Michel, the floor is yours.
Thank you, Christophe. So let me share the screen. Is it okay for you?
Yes, that works.
Okay, so thank you. First of all, I'm very pleased and honored to be with you today for this presentation. Thank you, Lab Quantique, and I would also like to thank Ecole Polytechnique and Quantique, the alumni group devoted to quantum technology. So a few words about me. So I am Michel KUREK. I spent a couple of decades working in the quantitative finance industry, and I have recently decided to shift my career to be as close as possible to scientific and technological innovation. I started my initiatory journey 6 months ago by carrying out this study that is with the subject of the landscape of quantum technology. And I will show you some elements now. So please note that this study is purely academical, and one of the purposes is to feed actually the quantum ecosystem with up-to-date data and insights. So let's dive into it. So I'm afraid we will have a lot of figures. So let's take first some key takeaways. My study consists of 4 parts: patents landscape, publication activity, public and investment, and private investment, and all those subjects were addressed between May and July 2020. And the considered historical period is 2010-2020. Regarding patents, I counted about 10,000 patents whose subject is about quantum technologies in general, out of which 52% are Chinese. The combined share of the US and China is 3/4. The number of scientific publications dealing specifically with quantum computing now is 16,000. American papers represent 26%, and China is slightly less. For public plans and investment, I listed 17 initiatives, out of which 10 include investment about $1 billion over 5 to 10 years. And regarding private investment, the study focused on the risk capital, which amount to $1.5 billion since 2012 and 300 deals. Almost 70% of the money flow went to North America, and Europe share is 17%. So let's go into more details now for some of these points. We start with patent landscape. Okay. The objective of the study was to have a better understanding of the patents landscape. This kind of study is proven to a good way to assess the economical potential of new technologies and to evaluate the dynamic of the transposition of the fundamental research results into new products. So in this study, I give a lot of KPI in terms of time evolution, in terms of location, in terms of applicant names, and I propose to go over some of them. First, a couple of slides about the methodology. My initial choice was to use the commercial patents database called Orbit from Questel. Regarding the areas of interest, I took the usual 4 pillars: sensors, telecommunication, simulation, and computing. And honestly, getting the adequate research equation was a challenge in itself. About the query, I tried to be as much exhaustive as possible without being overwhelmed by false positives. Of course, it's not perfect. Some patents certainly slip through the cracks. So I selected a bunch of pertinent keywords. Then I use them for searching into the titles, abstracts, and claims to find pertinent patents. So in addition, I use also patents classification code, IPC and CPC, and of course, filing dates, and that's it. So by doing that, you get a set of patents which can be classified according to their international patent categories. In fact, the tree-like structure of patent categories linked to quantum technologies is pretty large. It involves physics, electricity, and also application fields. interesting fact is that a specific code has been introduced in 2018 for quantum computing. So namely, it's the G06N10. And previously, such patents were attached to a miscellaneous category. So let's share some analysis now. First, it is important to know that it is not possible to get an accurate number of very recent patents because of a legal delay period of 18 months applicable to the patent publication. So I have identified 13,000 patents since 2000, out of which around 10,000 were published between 2010 and 2020. After a period of stability between 2000 and 2009, the number of patents began to increase, particularly from 2012 onwards. The constant annual growth rate is 19% between 2010 and 2018, and it rises to 27% when we consider the last 5 years. And lastly, 1,800 patents were published in 2018. Great. If we look at the recent evolution by technology fields as defined by IPC code, we can see the increasing share of quantum computing and quantum communication. So almost all the 700 here patents in communication in 2018 were actually about quantum key distribution. The other domains were quite stable over the last year. Regarding the geographical distribution, it is a case, as it is a case in many other sectors. China has become the world leader in terms of patents field over the period. Almost 5,200 patents for China, which is 52% of the patents. When we compare the Chinese number to the American one, we can see that 2012 was a pivotal year once again. A total of 50 countries has been registered as applicants, and Asia is 64%, with China, Japan, Korea in the top 5. Europe is between 8 to 13%, depending on the boundary we take for Europe. Next slide. So here we have the distribution of patents by countries and technology, and it shows clearly that the quantum world is split in two parts. On one side, we have China, on the other side, we have the US, and Europe is between the two, so in the middle. China has become the leader in the field of quantum communication. We know about the Quest and MOSI satellite program and their ambition to build 35 kilometers quantum communication networks. The USA remains the leader in building a quantum computer, clearly. And if you look at Europe, you will see effectively they are pretty much on the computer side, but it's less clear than US and China breakdown. The last word on this one, China's first place is not specific to quantum technology. China is also the leader when considering all types of patents. This slide is about the distribution of patents by applicants or assignees. We count 2,800 applicants for the 10,000 patents of our database. Top 20 players, key players, account for 20% of patents, and 11 out of the top 20 are Chinese organizations. And the first one is actually FOREMAN Quantum Technology, which is specialized in telecommunication. Note that we must be cautious here because it can be difficult to get accurate numbers, considering that some typos or variation in the name of the company are pretty frequent. So here this slide show for each of the top 20 applicants, all the different fields of their patents. Bubble size is proportional to the number of patents. And we can find again the split in terms of technologies between Chinese and other applicants. It is interesting to see also at the bottom that there is Chinese university, and there is only Chinese university that are appearing here. We don't have US or European university. For sensor and metrology, unsurprisingly, we find names like Micromass and Thermo Fisher. And also, I emphasize here the activity of AGCC, as it is the subject of the next slide. So I try to be quick on this one. This slide shows a collaboration between organizations, which leads to co-patenting. In my study, I spot the light on AGCC, who operates the Chinese electrical grid. So it's the world's largest grid operator. And since 2012, the company has been focusing on quantum technology, with their main objective being to secure their power grid communication. So they have a strong link with USTC, and they own now almost 100 patents in the quantum technology field. So not only communication, they have also some measurement and also a little about computer technology. So this view is interesting as it shows how the citations between patents are both clustered by technology fields and also by location of applicants. We find again the telecommunication in China on one side, even if we have Toshiba here in the middle. We have here the quantum computing subject, mainly with North America. And of course, we have a specific here cluster with sensors and metrology. After the first part of this study related to quantum technologies in general, let me share with you 3 more slides specific to quantum computing. So since 2012, 1,550 patents has been filed with IPC code explicitly related to the quantum computer. And the number are up 49% per year in average, which is represent an 11-fold factor since 2012. Same issue, of course, in terms of delay in patent publication. If we look at the geographical breakdown now, we have 32 countries that has filed at least one patent since 2010. The 20 most active countries account for 98% of patents filed. Top 5 is 81%, and top 10 is 94%. We see that it's pretty concentrated. The USA account for 56% alone, and together with Canada, North America represents 61% of the patent application. Europe is very broadly speaking, account for 14%, out of which European Union is 9% or so, with 143 patents. UK organizations hold 65 patents, which is about 4.2%, and Swiss organization is hold 33 patents, which is around 2%. Well, the next slide shows now the 39 organizations that hold more than 6 patents at the time of the study. So 45% are held by top 10 applicants, and even 33% by the top 5. It's not surprising that IBM is a key player in the sector, but the typologies of player is quite diverse. If we look effectively in terms of typology, we have a list with different categories of players. We have US IT giants, so IBM, Intel, Microsoft, Google. We have some Asian conglomerates with Hitachi, Toshiba. We have startups specialized in quantum computing hardware like D-Wave, Rigetti, Origin Quantum, IonQ, C-Quantum, and a couple of software, 1QBit and Zapata. We have also FA Origin Quantum, a Chinese startup, the first for this country, which is positioned on a full stack offer. And we have also, in terms of sector, defense and security sector organization, with Northrop Grumman on the corporate side, US Navy and US Army on the military side. And also we have some civilian agencies like Sandia working with the government. Finally, we have academic sector, which is well represented with 12 institutions of different nationalities, half of which are American. So a quick wrap up for this part. We saw numbers, we saw the key countries, the key players. One last thing, we must qualify our observation by noting that the fact that filing or not filing a patent is considered differently depending on the country, but this one is another topic. Now I will show you some extract on the study that I did on the research publications, so working paper, scientific paper. This part is an extract from the study, and I engage you effectively to download the study if you want more information. So in terms of objective, the objective was pretty similar. I won't go into too many details. The objective was to qualify the interest of the scientific community by looking at the evolution of the number of publications, their impact in terms of citations, geographical distributions, the most prolific organizations, the most prolific author, and so on. So for further information, don't hesitate. I put the link at the bottom of this slide. Just some general metrics about this study. So the database contains 16,000 publications. I use Scopus as a database. The average annual increase was 10% over the period. And the top 10 most prolific countries account for 99% of the publication. USA and China are the first two countries. I also did some good analysis of collaboration, and also in terms of author, I engage you to have a look to see who's who about the top 10 authors in this field. Here is the last part of this presentation. It is about the private investment landscape. The amount of investment are generally difficult to assess, except when they are made public by the company's communication departments. But data on investment made in startups by private investors or public funds are sometimes available in databases such as PitchBook or Crunchbase, which are the database that I use for this study. So over the period 2010 to 2020, we get 300 transactions concerning about 100 startups that has been identified. We can see from this chart that from 2012 onwards, that investors began to take an interest in startup in the sector. The year 2017 was particularly active with more than $300 million invested, almost threefold the previous year number, mainly in quantum computing hardware. 2018 and 2019 marked a step back with around $200 million, but the first semester of 2020 has been exceptional, so a very good resiliency despite the COVID. In total, since 2012, we have $1.5 billion that has been invested and disclosed in quantum technology startup. Nearly 2/3 of the declared investment were devoted to 15 hardware companies and 19% to software companies and so on. So this slide completes the previous one with the number of deals per year. The picture is a little different here. The number of deals has increased since 2015 with a strong acceleration in 2018 when many small investments were made. View from this angle, it's software companies that benefit the most. This slide now gives some precision about money flow. The details about startup names and their location are given in the report. The top 3 names are Quantum, with a jumbo deal this year, D-Wave and Rigetti, the 2 of them being on the award side. If we sum up the numbers by region, we show that venture capital investment in North America represents 70% of the total investment. It is now quite instructive to detail the breakdown of the investment made in the hardware company aiming to build a quantum computer according to the type of qubit technology they are using. Californian startup Quantum plans to develop a photonic quantum processor. Alone, the company has received almost $300 million, out of which 230 million this year. This explains the large share of funding for photonic platform, which is 36%. We know that there is a couple of other companies working on this technology, like Xanadu or Orca Computing, for instance. There are many more players on superconducting qubits beyond the $225 million invested in startup. We know that major players like IBM, Google, etc., are investing also in that technology. Then we have D-Wave, which falls into the annealing computer. And D-Wave has received more than $200 million, which is representing 22% of the money. Trapper Ions platform company raised $88 million, most of which were allocated to IonQ in the US. But we have also the Austrian startup Alpine Quantum Technology, who had some grants last year for $11 million. And then the Australian startup Silicon Quantum Circuit has received $66 million since its creation. It is interesting to compare the result of the survey with a survey conducted last year by Michele Mosca among 22 professionals in the quantum technology sector. The question was to rank physical implementation with a specific goal of achieving a digital quantum computer with 100 logical qubits within the next 15 years. And the responses indicates a fairly general consensus that the preferred platform are superconducted system and trap ions. But this result is in line with the investment made with a striking exception of photonic quantum computers. So it suggests that while the technology potential is certainly high, the investment seems very speculative for this type of qubits. So, it looks like the final bouquet. So in fact, it's an illustration of the capital links between venture capital firms and startup. And I have highlighted the case of Cantonation, the French investment fund specialized in deep physics, we all know, and the case of D-Wave. So the last slide. Last words. So the quantum race is ongoing. Western and Asian governments are rolling out strategic plans with the fundings as the sovereignty issues are taken into account. China and USA are ramping up with fantastic technological developments, going out of the lab with the help by money flowing. And I hope it's not too late for European countries to catch China and USA. So that's it for me. Thank you.
Thank you, Michel. Thank you very much. Very impressive work. I think we've been very pleased and honored that you decided to publish on our website. I think very happy with that. I think definitely we need more facts, data to design proper policies for quantum technology deployment, and that's the mission of the Lab Quantique. So we really look forward to further working with you and also collaborations on this kind of topic. So I've got a couple of questions. I think you've got 2 questions from Mathieu Repellin. If you can answer, maybe it's more specific to the slides. If you can answer in written in the Q&A, because we don't have a lot of time, that would be great. And another question, what were the most surprising takeaways that you came across whilst undertaking this study? And do you think that the majority of private investments made in quantum technologies are well informed? It's a good question.
It's for you. It's for you, this one. Actually, it was for me. It was really an initiatory journey. So, in terms of surprise, I think it was the place of China, because it was at the beginning of my study. It was quite impressive, and I think it's something that is linked to what I said. The fact that some countries are publishing and want to publish some patents is specific, and we know that Chinese university has some KPI in terms of patent publication. So, and it seems to me that 2012 is a pivotal year in China, because it's the beginning of this quinquennal plan, which puts some pressure on the university in terms of KPI like patents. So it's not just this one. I think there is also a lot of technological breakthrough around this year that explain why investors, why we see so much patents, so much publication going up. But it's on the Chinese side, I think it's a good explanation in terms of political plan, quinquennal plan.
Okay, thank you. Well, I think we're, so there was Emily's question, that's the one I was thinking about, but maybe just this one again. Do you think that the majority of private investments made in quantum technologies are well informed? Do you think private investors know as much as they should to make wise decisions in the space? So I can answer this one, but I'll leave it to you.
I don't know, because effectively, I'm not sure that all the venture capitalists has the competencies that you can have here in quantumation, and so it's pretty difficult for me to answer.
Thank you, Michel. No, anyway, I think maybe I can just say a few words to Emily. I think it's also something that motivates actions like we do at the Lab Quantique to share good practices, information. I think people need to make good decisions, obviously, and that's progressing fast, and I think it's good. But it's revenue technology, so people need to learn. So thank you very much, Michel. I think there was an additional question from Mathieu. If you can answer in written in the Q&A box, I think that's going to be good. And we will have Cameron Foreman from CQC telling us about something very different, but kind of pretty natural as well for quantum technology. So QRNG, combining also elements from quantum computing. So Cameron, the floor is yours.
Brilliant. Thank you, Christophe. Can you see my screen?
Yes, that's good. I think you can, if you can go in full screen mode, I think, yeah, that's it.
Is that all okay? Perfect. Yeah. Thank you, Christophe. And I'm really excited to share some of the work we've been working on recently with you all. So I'm going to talk about verified randomness from IBM's quantum computers. So there are many directions I could have taken this talk, but I've decided to focus on what makes verified randomness special, and that's the science. So before I really get into it, I'm going to talk about a few of the commercial implications of this. So, as some of you might have seen in the news, in collaboration with IBM, Cambridge Quantum Computing have announced this verified quantum random number generator. At the moment, it's exclusive for IBM Q Premium customers, and it's free to them. It's been integrated into IBM's Qiskit library, so it's super easy to run. You just need to import QRNG from Qiskit, and then you can start generating some outputs. At the moment, this implementation is a beta version, so in time, a full commercial offering will come, but it's just a preliminary version out for testing. So let's begin. And I'm going to start by talking about why randomness is important. So randomness in the real world is used in many different applications, from things like Monte Carlo simulations to gambling to cryptography. And in cryptography, we have the most stringent definition of randomness. We need the highest quality randomness. So randomness used in cryptography can be used in all other applications. So we'll focus on this. So cryptography is this field of secure communications. For example, things like encoding and decoding information. In cryptography, the security of our information is based on the quality of the randomness we used. And so this leads to a really quirky game of cat and mouse. So here's our game of cat and mouse. You may recognize them as Tom and Jerry. So on one side, we've got Tom. He's our hackers. So these are the people trying to get access to our important information. On the other side, we have Jerry. These are the cryptographers. These are the ones trying to keep our information safe. So in practice, sometimes the cat does catch the mouse and our hackers get access to our important information. This then obliges our cryptographers to come up with new ways of keeping our information safe. But the aim of the cryptographers is to win this game and stop the cat from ever being able to catch up and get access to this important information. So how could we win this game? So winning this game, at least in terms of randomness, is to build a random number generator that produces unpredictable random numbers. By unpredictable, I don't just mean unpredictable to you or me. I mean unpredictable in the sense that anyone, even with the most powerful quantum computer that's fully functioning and has infinite computational power, it's still unpredictable to them. Secondly, we need that our random number generator verifies it's functioning properly. So we want it to give us some certificate to say that the numbers that it's outputting are these unpredictable ones. And the question becomes, is this actually possible? Here's the problem with, here's a cartoon to illustrate the problem with random numbers. I'll give you a few seconds just to read it. So as you can see from the cartoon, sometimes we get outputs from random number generators that don't look random. For example, 999999. And this is the problem with randomness. A true random number generator has a chance to output any string of numbers. So from random numbers alone, we can't say anything about the randomness. So what can we do? Some of you may have heard of John von Neumann. He was one of the most notable mathematicians in the 1900s. And he said, there is no such thing as a random number. There are just methods to produce random numbers. And a strict arithmetic procedure, of course, is not such a method. He sums it up really well. We can't say anything about a random number itself. Instead, we just must verify that a process is producing random numbers. And that's exactly what we do. We get verified random numbers from IBM's quantum computers. So for this talk, I'm going to give some intuition of what randomness is and why it's important. I'm going to talk about the different approaches to random number generation and ultimately some of their limitations and why we need this new approach. And then I'm going to talk about verifying a process rather than verifying some numbers. And finally, I'll talk about actually the practical element, achieving this on IBM's quantum computers. So we'll start, what is randomness and why is it important? I'm going to start by giving an example. So in cryptography, we have this secure means of sending messages called the one-time pad. And in this setup, we have Alice. She's somewhere and she has a safe space in which to perform encoding of her message before she sends it to her friend Bob, who she wants to send the message to. And Bob is somewhere else. So somewhere else in the universe, Tom's back. He's our hacker. He is trying to access Alice's message she wants to send to Bob. But Tom isn't just any old hacker. He's our quantum hacker. So he has this fully functional quantum computer, which may one day exist, that has infinite computational power. And Alice wants to keep her message safe from him. So back to Alice. In her safe space, she has her message, which is these 5 zeros over here. And she, using this one-time pad, we need some random key. This random key must be the same length as the message itself. So in order to use the one-time pad, she encodes her message by summing each bit of the message and the key together individually. So doing this, we sum the first bits together to get 0, second bits to get 1, etc., until we get this new encrypted text. This is what she sends to Bob. And this is what Tom, our quantum hacker, has access to. So he can see this. But to Tom, this encrypted text looks random because Alice has used a random key. But as soon as Tom has some predictive power over this random key, it's no longer random. This encrypted text is no longer random to him, and he can gain information about Alice's message. This means that it's so important in cryptography to use secure randomness, even against our unbounded quantum hacker Tom. So what does it mean for randomness to be secure? Secure randomness is equivalent to being unpredictable. And as I said before, it's not just unpredictable to the user, it's unpredictable to someone with a fully functioning quantum computer and infinite computational power. So in talking about unpredictability, we need two concepts. These are the concepts of unbiasedness and privacy. So unbiased is that even to our all-powerful quantum hacker Tom, any outcome has the same chance of occurring. Privacy means that only the user is able to see the random numbers that are generated. Let me explain by giving some examples. So first we'll talk about unbiasedness. So why do we need unbiasedness when talking about unpredictability? So let's think about flipping a coin. To Alice, she's flipping a coin and using this to generate random numbers. To her, she gets around 50-50% chance of getting heads or tails, and they don't appear to be ordered. So to her, this seems unbiased. However, to our unbounded quantum hacker Tom, he has infinite computational power, so he can model the hand that's flipping the coin, he can model the coin itself, and he can even model the atmosphere the coin's being flipped into. So he gets some predictive power over the outcome of this coin flip. So to him, it is now biased. So this is why it's so important that even to our quantum hacker Tom, the random number generator remains unbiased so that it's not predictable to them. Secondly, we'll talk about privacy. So why does unpredictability need privacy? In this, we've got the setup with Tom. He has his own random number generator. Tom's random number generator is perfectly unbiased. So even to another version of Tom, it is unbiased. And he uses this to create some random numbers and put them on a memory stick. Now, we'll go back to Alice. So Alice is in her safe space and she's got some random number generator and she's generating random numbers with this. So if this random number generator is based on the memory stick that Tom put his unbiased random numbers on, it means that even though the random numbers Alice are getting are completely unbiased, they're now shared with Tom, so they're no longer private, which means Tom can fully predict them, which is not good in terms of security. So we've talked about what it means to be random and why randomness is important. So now I'm going to talk a bit about the different approaches to random number generation and ultimately some of their limitations. So random number generators have been around since Roman times, and things like flipping coins and rolling dice have been used for things like gambling, and they're based on physical processes, like a physical action classically. And as time's gone on, these processes have got harder, so things like thermal noise and a diode to generate random numbers. But ultimately, to our quantum hacker Tom, these are based on computational assumptions. If he can model enough about the scenario, he gets some predictive power over these random number generators. So in order to be secure against our quantum hacker Tom, we need a new approach. This new approach comes with quantum. So in quantum, we get intrinsic randomness that's based on physical, not computational assumptions. So randomness that even with this infinite computational power can't be predicted. So in principle, using these quantum effects and quantum processes, if we can build a perfect quantum process, we get unpredictable numbers, even in the case of our all-powerful quantum hacker. So let's look at the first approach to quantum random number generations by using an example. So here we have a quantum process. So here we have a laser. It's shooting photons at a mirror. 50% of the time they go through the mirror, 50% of the time they get reflected. And if they go through it and lands in the detector and gets detected, it's a 0. And if it gets reflected, it's a 1. And this generates our output. So in this physical process, if it comes down to, do we trust the device is working how we think? Because this is a quantum physical process. So there's intrinsic randomness in it. But as soon as the device stops working exactly how we think it does, for example, one of the detectors isn't as efficient as we expect, this introduces classical noise to the system. And this classical noise gives our unbounded quantum adversary Tom some predictive power over our system. So it no longer means that we have this only intrinsic unpredictable randomness. This is a problem because in practice, quantum is great, but it's noisy, especially at the moment. And so building a perfect quantum process is completely impossible. So we need something new. We need a way to not have to trust the device. And this is exactly the process we look at. This is the new approach. This is the solution. And we're able to produce unpredictable random numbers using this intrinsic randomness from quantum processes. But we also create an approach which verifies that the device is functioning properly. So we no longer oblige us to trust the device. So we've talked about what randomness is and why it's important. We've talked about the approaches to random number generation and the limitations of this, and a new way to generate random numbers, which verifies the process. So now we're going to talk a bit about verifying this random number generating process. So in this setup, we have Alice back in her safe space. She has some random number generator, but she doesn't really know what's going on in it. She doesn't care about the internal workings. She gives it some inputs and it gives her back some outputs. And from these inputs and outputs, she wants to be able to certify something is happening in this device and we're getting some unpredictable randomness. Somewhere else in the universe, we have Tom, our quantum hacker, and his job is to try and predict these outputs that Alice is getting. So the task is to verify that Tom cannot predict Alice's outputs. And in order to do this, we need quantum. So quantum correlations are something that is exclusively quantum, and there's certain correlations between inputs and outputs that can only exist if the device was using a quantum phenomena called entanglement. So if we can show these quantum correlations, we can actually limit the predictive power of our hacker. So by not looking at anything in the device and just looking at these inputs and outputs and showing these correlations, we can limit the predictive power of Tom. So how do we actually do this? So we want to test the device's response to make it oblige itself to show us if it's using this phenomena of entanglement. So in order to test it, we give the device many inputs and receive many outputs from it. So we do this many, many times to get many input-output combinations. Once we've done this, we check whether the device exhibits these quantum correlations we're looking for. And so what are the consequences of this test? This test, if we are able to show these quantum correlations, we get proven unpredictability because of this phenomena where obliging the device to show that it's using these intrinsic quantum effects. And if we fail this test for quantum correlations, we abort the protocol. So it obliges the device to only give us an output when we get this proven property of unpredictability. So we've talked about all the building blocks we need now to put this into practice. We've talked about what is randomness and why it's important. We've talked about the approaches to random number generation, and ultimately this new approach. And we've talked about verifying a random number generating process. So now let's get into the practical element, achieving verified randomness on IBM's quantum computers. The task. to obtain verified random numbers on today's noisy quantum computers. We start with an imperfect random number generator. So this is something Tom has some predictive power over. So it could be biased to him, or it could be not private. And a good example of this is this beam splitter we used earlier, this laser and mirror creating a quantum random number generator. Because we couldn't intrinsically characterize it, there could be bias in it. So this would make for a great imperfect random number generator. So once we do this, we use this to drive a quantum computer. So this is relating exactly to this game we were playing before, this test for quantum correlations. So this imperfect random number generator gives us the inputs to drive the quantum computer to get outputs to look for these correlations. Once we've done this many times, we submit these input-output combinations to verification. And in this step, we want to check for these quantum correlations. And if we do get these quantum correlations, we do some post-processing to completely get out the proven unpredictability we had in the final step. I'm not going to get into that too much, but and as the final output, we get verified, unbiased, and private randomness. So let's recap. What have we done? We've started with imperfect randomness, and at the output, we've made it perfect. So we start with some imperfect randomness, and the scheme takes care of the rest. This means fundamentally that it doesn't oblige us anymore to make perfect random number generators. Instead, we can accept that building a perfect quantum process is hard and just build something imperfect and let a scheme like this take care of the rest to get perfect verified output at the end. So in conclusion, what we've done is we've taken a really novel approach to random number generation. We've verified randomness with quantum resources, specifically this idea of quantum correlations. We've no longer obliged the user to trust the device. We let the device self-test so we know when it's functioning properly. And we've also shown a real-world use for today's noisy quantum computers. What does this mean? So this means we've created a random number generator that produces this unpredictable random numbers and also verifies that it's functioning properly. This means, at least in terms of randomness, we've ended the game of cat and mouse. So I've kind of given a flavour for what's going on here, but if you want more technical details, here's a link to our paper, and I'm happy to answer any questions. Thank you for listening.
Thank you, Cameron. Thank you for a very nice introduction to RNG, also very practical. Well done. I don't see questions here. I have one, so it's in relation with the quantum computer itself. So how does the performance, the quality of the quantum processor impact the performance of your device, verificability and the quality of the randomness? How is it related to the quantum processor itself?
Great. So really good question, Christophe. So in terms of the performance of the actual quantum device itself, this relates to the assumptions we can place on this imperfect random number generator. So if we have a less noisy, more perfect quantum device, then this means we can really push this imperfect randomness close to almost completely predictable to our quantum hacker. But as the device gets a bit more noisy, it means we require a bit more unpredictability in the source.
Mm-hmm. Okay, very clear. Thank you very much. And do you have corporate customers already for the new offer associating IBM and your technology at CQC?
Unfortunately, I can't really comment on that because I'm one of the scientists. So I think that's a business question. So sorry.
That's good. No, thank you very much. No problem. Look, I don't see a question, so I think it's also the end of the session. So I think we're good. Thank you very much to our speakers. So Michel, Cameron, and Irfan, who were to leave us a little bit earlier. Thanks everybody for attending today. So everything will be posted, the presentations and the video tomorrow, most probably, and you will receive an email also. And looking forward to see you very soon at one of our next sessions. Thank you. Have a great evening. Bye-bye.
Thank you. Bye.